Welcome to lesson 7.02. Here we're going to approximate the area under a curve by applying a trapezoidal approximation method and interpret the results in real-world contexts. To get started, go ahead and complete this problem and all the parts A, B, and C on your own. You can use either of the three methods that we've learned in the previous lesson, and make sure to use a graphical representation that'll help you with the other parts of the problem. Work through that first on your own, and then we'll discuss. So I decided to use a left endpoint Riemann approximation, and in doing so I found that the approximate area underneath the curve from 0 to 2 is about 4.924. If you did a right-hand rectangular approximation, you would have gotten something around 8, and if you used a midpoint approximation, you would have ended up with something around 6.32. Now, regardless of which one you used, when you've drawn out this graphical representation, you should be able to see that this approximation is going to fail to give an exact area under the curve. And the reason that is that for each of these approximations, we're leaving out a bit of the true area underneath this curve. We can see each of these left out pieces if we focus in on any subinterval. So consider the subinterval from 1.5 to 2, and notice that we're approximating using the area of this rectangle. But if you look at the area underneath the curve itself, we can see that this area is not a perfect rectangle. And that should be pretty obvious, and whenever we use a rectangle, we're going to be treating the function as if it is perfectly horizontal on that interval, right? So the area under it is the area under a rectangle. But obviously this curve does not have a perfectly horizontal, is not perfectly horizontal on this interval, and so it's not going to be exactly the same as the area in this rectangle. With that in mind, we want to think about making our approximation better. So what other geometric shape could be used instead of a rectangle that would get us closer to the exact area? So hopefully you noticed that the missing piece looks very similar to a triangle. And so if you were to take a triangle and put it on top of any of these rectangles, you would get a much closer approximation. Well, what happens if you take a triangle and you put it on top of a rectangle? What kind of a shape do you end up with? Well, pending that the base of that triangle is the same as the base of the rectangle, you're going to end up with a trapezoid. So let's take a look at what a trapezoidal approximation would look like. All right, so here's a trapezoidal construction, and to figure out how we created these trapezoids, it's probably easiest to look at the last trapezoid here. So notice that the way that this trapezoid was constructed, the trapezoid of course has two parallel side lengths and then straight lines connecting the ends of those two side lengths. So the left vertical side length is the value of the function evaluated at the left endpoint of that subinterval, and the length of the right vertical side length of my trapezoid is the value of the function evaluated at the right endpoint of my subinterval. And then here we have the length of the subinterval, and then we're connecting those two left and right vertical side lengths with a straight line. And so that's our trapezoid. And a trapezoid, of course, is made up of two parallel sides, and then those two parallel sides are connected at the ends with straight lines. So if I pull this trapezoid out, we'll be able to take a look at what the area of a trapezoid, how do we compute that? Okay, so here I've pulled out my trapezoid, and the area of a trapezoid, what we want to do is we want to take a look at the two parallel side lengths, and we want to find the distance in between them. And we're going to take that distance, which happens to be 0.5, and we're going to multiply it then by the average of the two parallel side lengths. So we'll take this side length and this side length, we'll add them together, divide by 2, that'll give us the average of these two parallel side lengths, and multiply by the distance between them. And so there you have the computation for the area of this particular trapezoid. Notice that it requires a little bit more work than the area of a rectangle, but as we can see, it will give us a better approximation than we had previously. So let's go ahead and use this trapezoidal approximation then to make a more refined computation. So here's the trapezoidal approximation, and I'll just walk through very briefly the first trapezoid here. So the first trapezoid has a left vertical side length of e to the 0, and then the right vertical side length is the value of the function at that right endpoint, which will be e to the 0.5, and I'll take the average of that by adding them together and dividing by 2, and then I'm going to multiply by the distance between the two parallel side lengths, which for any of these is going to be 0.5. So multiply by 0.5. And I do the same thing for each of the other trapezoids as I go through. Notice that this last one is the same as the one that we discussed in detail. And this computation looks like it could be a real pain, but if you notice, this is e to the 0 plus e to the 0.5 divided by 2, and then you're multiplying by 0.5, which is just the same as multiplying by 1/2. So you'll have 1/2 times another 1/2, which is just 1/4, and you'll have a 1/4 multiplied by each of these sums here. So you can factor out a 1/4 from the whole thing, and that would make your computation quite a bit easier if you are looking to be a little more efficient. And we get a value of approximately 6.521, which we can see is different than the left endpoint rectangular approximation. And this trapezoidal approximation, as we can see, is a good bit more accurate. So 6.521 is going to be a lot closer to the true area underneath the curve of e to the x on the interval from 0 to 2. Let's go ahead and formalize our trapezoidal approximation method. Okay, so you'll notice that the trapezoidal rule for approximating the area under a curve is very similar to the rectangular approximation methods. We're still working with non-negative functions here, and we want to approximate the area underneath the curve but above the x-axis between a and b. And what we're going to do is we're going to split up our interval from a to b into n equal subintervals, and then on each of those subintervals we're going to approximate the area under f using a trapezoid, where the distance between the parallel sides is the length of the subinterval, and the length of the parallel sides are given by the value of the function f evaluated at the left end and right end points of the subinterval, respectively. So let's just quickly draw that out so that we make sure we know what we're talking about and we can go ahead and apply it. I first want to split this up into n equal subintervals. Just as we did before, I'll split this up into 4 equal subintervals. So here I've split up into 4 equal subintervals, 1, 2, 3, and 4. Now in each of these subintervals, I'm going to construct a trapezoid, and the distance between the parallel side lengths, so I'm going to have 2 parallel side lengths coming down here, and the distance between them is just the length of the subinterval, and we call that, of course, delta x. We're used to that notation. And then the length of the parallel side lengths are going to be given by the value of the function f evaluated at the left end and right end points of the subinterval, respectively. So the left end point of this first subinterval is going to be the value of the function is right here. Then the right end point over here, the value of the function is going to be this value here. So those are going to be the parallel sides. And then, of course, the trapezoid is completed by connecting the two endpoints of these two parallel sides. We've already connected the endpoints of these two parallel sides with just the length of that subinterval, and we'll connect these two here. So there you have our first trapezoid, and we know that we're going to take the area of all the trapezoids and add them together to find the approximation for the area underneath the whole curve. So to refresh our memory, as we just did previously with the area of a trapezoid, let's go ahead and write that down first for this first trapezoid, and then we'll go ahead and finish out the rest. So remember, what we're going to do is we're going to take the average of the 2 parallel side lengths, and then we're going to multiply by the distance between them. Okay, so that's the area of the first trapezoid. Here's the average of the two parallel side lengths, and then multiplying by the distance between them, which is just delta x. All right, go ahead and try writing out the rest of the trapezoids and adding their areas to the first one. All right, so there we have the final product of a 4 subinterval trapezoidal rule approximation. And nothing should be out of the ordinary here. Just notice I've written f of b instead of f of a plus 4 delta x, because clearly if I add 4 of those delta x's, I'll get all the way to the value b. All right, so let's go ahead and apply this to some situations. Problem number 1. A ship travels with a velocity given by the function v of t, which is equal to 3t squared, measured in nautical miles per hour. Use a trapezoidal approximation with 4 equal subintervals to estimate the total distance the ship travels from t equals 1 to t equals 2. Go ahead and complete this on your own first, and if you're interested, you might also do a left rectangular approximation or right rectangular approximation, or even a midpoint approximation, and compare it to your trapezoidal approximation. All right, hopefully that went well. Just by reading the problem, I can tell that I'm going to need to find the area underneath the velocity curve in order to figure out the total distance that the boat has traveled between that time of 1 and 2, 1 hour and 2 hours. And I'm going to use a trapezoidal approximation with 4 equal subintervals. So I went ahead and sketched a graph. Of course, you don't need to if you are feeling really comfortable with this situation here, but particularly for a trapezoidal approximation, it will be helpful to visualize each trapezoid so that we make sure our calculations are accurate. All right, here are my trapezoids. Notice that I've split up this interval from 1 to 2 into 4 equal pieces. So that means that each subinterval has a length of 1 divided by 4, or 1/4, 0.25. And now I'm able to go ahead and calculate the area of each of these trapezoids and then add them together. So if you haven't done so already, go ahead and do that now, and then you can check your work. So there are the calculations for each of the trapezoids and then added together. A couple of things to make your computation quick is notice that 1/4 times 1/2 will be 1/8. So you'll have a 1/8 with each of these terms. So you can factor out that 1/8, and you'll have 1/8 times, and you'll just have all of these different v of 1, v of 1.25, another v of 1.25. That'll be 2 v of 1.25. So if you think about it, it'll be 2 times 3, which is 6, and then 1.25 squared. And that'll make your life a heck of a lot easier when you're computing this value. But if you don't want to, you can just do each of these and add them together, and you get 7.031. Now we need to make sure we're interpreting this in terms of the question asked, and the question is asking the total distance that the ship traveled, and of course this is the total distance the ship traveled in nautical miles. And those nautical miles that it traveled occurred between t equals 1 and t equals 2 hours. All right, now go ahead and move on to the homework 7.02.